In this video, we're going to take a look at section 2.1, Introduction to Limits. All right, so let me start off by saying, chapter 1, I was really familiar with all that material. It's all college algebra stuff. Now we're venturing into the calculus concepts, which I haven't taught in some time. So this is not going to be very polished. I might be kind of learning along with you here as I refresh my memory, but I'll do the best I can. All right. So we write lim, as x approaches c. All right, so that's down here. So that's how you read this part right here. So this lim is an abbreviation for limit. So this is read the limit as your x variable approaches the value c. So c will be a number, right? C typically would not be a letter. So it might be x approaches 0, x approaches 1. So the limit as x approaches c of f of x equals L. So that's one way of writing the limit, which is probably the way I'm going to be writing them, because this just seems like more work over here. But this means the same thing. It's the same thing as saying f of x approaches the value L. So again, L will be a number. Or it could be infinity. We'll see that in a later section. It shouldn't be infinity in 2.1, I'm pretty sure. All right. So f of x approaches some value L as x approaches c. You can write it like that as well. If the functional value f of x is close to the single real number L, whenever x is close but not equal to c. So we're trying to determine the value that f of x approaches as x approaches c, right? So your value of x will get closer and closer and closer. So for example, if we're looking at the limit as x approaches 2, we'll be interested to know, well, what does f of x equal for 1.5, 1.6, 1.7? As we get closer and closer to the number 2, but not what it equals if you plug the number 2 in directly. We just want to figure out what is it approaching as we get closer to x equals 2. 1.9, 1.99, 1.999, right? You can also go from the other direction, 2.1, 2.05, 2.04, 2.03, to see what the value approaches if you are approaching from the right-hand side of 2. In fact, we'll have to be kind of considering both options, right? The existence of a limit at c has nothing to do with the value of the function at c. As I just mentioned, if we're trying to find the limit of f of x as x approaches 2, we're not going to plug 2 into the function. That's not what we're evaluating. We're trying to see the value that f of x approaches as we get closer to the number 2, but not exactly equal to 2. So in fact, c may not even be in the domain of f, which means c might be a number that you're not even allowed to plug into the function. It might not even be a valid value of x for us to see if the limit exists. However, the function must be defined on both sides of c. So it needs to be defined at 1.9. It needs to be defined at 2.1 in order for the limit to exist. All right. Let's take a look at, we got a few definitions to get out of the way here. If I can get my mouse to click. Okay. So as I mentioned, we're going to be interested in seeing the value of our function as we get closer to a certain number for x. And we will be approaching that value from both underneath and from just above. So 1.9, 1.999. If we're looking at the limit when x approaches 2, and we're approaching that value of 2 by plugging in 1.9, 1.99, we're approaching from the left-hand side of 2, right? If you think of the real number line, 1.9 is just to the left of 2. So we'd be looking at the left-hand limit of that function as x approaches 2. And we indicate that by putting a little minus sign as a superscript here by the number. So we might have something like this, like the limit as x approaches 2. But if we put a little minus sign beside it, that means we're approaching 2 from underneath, from the left-hand side. So 1.9, 1.99, etc. And getting closer and closer to 2 with our choices for x. and that's called a left-hand limit. We will also be interested in knowing the value of our function as we approach x from above 2, or to the right of it if you think of the real number line. In that case, we will put a little plus sign indicator by the number. So it would look like this: the limit as x approaches 2, but from above. I don't know, for me, bigger numbers are above, smaller numbers are below, but we're actually trying to keep this more horizontal because the x-axis is horizontal. It makes perfect sense why we would want to do that. But I really properly should say as x approaches 2 from the right-hand side of the x-axis. So this would be choosing values of x like 2.1, 2.01, and getting closer and closer to 2 from that direction, right? And that's called a right-hand limit. All right. So for a two-sided limit to exist, the limit from the left and the limit from the right must exist and must equal each other. So that is, the limit as x approaches c of f of x equals L, again L being some number, if and only if the left-hand limit equals the right-hand limit, which equals L, right? So the limit overall will equal L as long as both the left and the right-hand side limit equal L too, right? So they have to converge, they have to agree basically. The left-hand limit has to agree with the right-hand limit that, hey, the value we seem to be approaching here is this number. And if that's the case, if they're in agreement, then the limit exists. The two-sided limit exists. So we don't have to put the plus or minus sign here. The general limit just exists as long as the left-hand limit agrees with the right-hand limit on what that value is, right? Okay, if they don't agree, the limit doesn't exist. Right. I'm sorry about that. Sorry about that. If there's extra additional noises that you're hearing, there's a loud car outside, and then I just hit my microphone with my pen by accident. All right, so let's consider this function here. This is kind of a crazy function. It has an interesting behavior to it. We want to know what the limit as x approaches 0 is, and that's a really common limit to look at as x approaches 0, of the absolute value of x divided by x. So in order to evaluate what this overall limit is equal to, we have to consider the left-hand limit and the right-hand limit. So I need to consider the limit as x approaches 0 from underneath, from the left-hand side, of this function, absolute value of x over x. So I want to know what's that equal to. And then I also need to consider the right-hand limit, which is the limit as x approaches 0 from above, or from the right-hand side of 0, of that same function, absolute value of x over x. So what we need to do is make a chart of values. Let me switch up the color here a little bit. What we'll do is we'll pick some numbers for x that approach 0. And you don't want to start from too far away. You don't want to start from like -5, -4. You want to be a little bit closer up to the limit that you're interested in. And so I would recommend starting, the furthest back you'd want to go is maybe like -1, right? And then maybe -0.5. We'll just use decimal numbers. I mean, we could use fractions, but it's just going to be messier. And then -0.1, and then -0.01. These would be getting pretty close to 0 from underneath, from the left-hand side of 0. And if you think of the real number line, right, 0's right here, the negative numbers are to the left, right? So we're approaching it from the left-hand side, getting closer and closer to 0 from this direction. And so that's -0.5, -0.1, -0.01. Now this function gives you the same answer every time. So what's going to happen when I plug in, let's start with -1. So ignore this for right now. Just plug it in here, right? So I'm going to take x equals -1. I'm going to plug it into that function. So we'll get the absolute value of -1 over -1. The absolute value of -1 will be +1. 1 divided by -1 gives me -1. So I get -1 here. If I plug in -0.5 into that function, I'll get the absolute value. So I'm plugging it back into this function here. I'm just plugging in a different number for x over -0.5. Again, the absolute value doesn't change the number. It just makes it positive. So we'll get positive 0.5 over negative 0.5. And even though it's decimals, the rule is if you divide by the same, if you divide a number by itself, you always get 1, right? So we're going to get 1 here, but positive divided by negative is going to make that negative. So we'll get negative 1 again. And I'll let you check the other two, but you'll find you get the same answer every time. You're just going to keep getting negative 1. So what is this function? So as we get closer, so here we're getting closer to 0. And this is my function, right? This is my f of x here. What value is it approaching as I head in this direction? It's really already there. It's negative 1. So that's the value it's approaching as I'm getting closer to 0 from the left-hand side. So the limit here is going to be negative 1. Right? That's the value that we are approaching. From the right-hand side of 0, right? So from over here, we'll have positive 1, positive 0.5, positive 0.1. That would be approaching 0 from the right-hand side. So we'll start at 1 because that's the furthest number away, and then we're going to keep getting closer and closer by picking smaller and smaller numbers as we get closer to 0. Plug that into this function here. We're going to get the absolute value of 1 over 1, which gives me 1 divided by 1, which gives me positive 1. If I plug in 0.5, the absolute value of that, divided by 0.5, we're going to get, sorry, I keep hitting the microphone, 0.5 divided by 0.5. Again, when you divide a number by itself, you get 1. And this time it's positive, right? We get positive 1. And you can check these other values as well. And we kind of see a similar pattern over here, but it's a different answer, right? So as we approach 0 from the right-hand side, we see that our function values, right, f of x, which is this function here, seems to be approaching the answer of 1. In fact, it's already there, right? It's already at 1, and it's just going to keep being 1 as we get closer and closer to 0. So the limit in this case is going to be positive 1, right? So the left-hand limit equals negative 1. The right-hand limit is going to equal positive 1. And so they don't agree, right? They're not agreeing on what value this function is approaching as we get closer to 0. If you start on the negative side, your point of view over there is that, oh, we're approaching negative 1 as the answer. So that seems to be the likely answer for when you get to 0. But from the positive side, the evidence we're seeing over there is that the likely answer is going to be positive 1. And since they don't agree, the limit does not exist. So this limit does not exist because these two do not agree with each other. All right, so maybe that's a bad first example, having an example where the limit just doesn't even exist. Let's look at some other examples here. So this one, instead of giving us an equation to work off of, we are working off of a graph. All right, so we have to be able to read the values we need off of the graph. Remember, f of x is your y variable, right? So what this is asking for here is the limit as x approaches negative 1. Now be careful, we kind of have a weird double negative thing going on here. It's as x approaches negative 1 from the left-hand side. So this is the left-hand limit from the left-hand side of negative 1. So negative 1 on the x-axis is right here. We want to see the value that this graph is approaching for the y-coordinates, right? We want the y-coordinates that it's approaching as we get closer to negative 1 from the left-hand side. So looking at the graph, we actually have kind of an interesting graph here. It's just a flat line, right? So again, we can make a chart, right? So let's make a chart like we did on the last problem. We are approaching negative 1 from underneath, from below the left-hand side. So we could start with negative 2, negative 1.5, negative 1.1. This one's going to have a similar feel to the last problem. Negative 1.01, right? That's getting closer and closer to negative 1. So this is getting closer to negative 1. That's what we're approaching with our x values. Looking at the graph, what's the y-coordinate for these numbers, right? So here's negative 2. The y-coordinate for that point is going to be 2. Sorry, I'm doing a bad job of writing on here. Let's try that again. It's going to be 2. For negative 1.5, we find that point on the graph, which is right here. The y-coordinate is also 2, so we're going to get y equals 2 there as well. And again, y is our f of x value, right? For negative 1.1, which is going to be pretty close to negative 1, we look at the graph, it's still 2, right? The y-coordinate is still 2. Same thing here, right? So f of x, again, it's approaching 2, but it's kind of weird to say that because we're already at that value, but it's not changing. So the value that it appears likely to equal as we keep getting closer to negative 1 is 2, right? As the x values keep getting closer to negative 1, the y values look like they're just going to stay the same, and we're just going to get 2. So the left-hand limit is equal to 2. So this was for the left-hand side, starting from the left-hand side of negative 1. For the right-hand limit, which is what we're being asked to find here because of that plus sign, so again, it's negative 1, but from the right-hand side of it, right, which is over here, this region right here. We can do the same thing. We can make a chart. We can pick numbers that get closer and closer to negative 1. We might start as far away as 0. You don't want to start too far away. We'll start at 0, right? And then we'll pick like negative 0.5, negative 0.9, negative 0.99, right? That's getting closer and closer to negative 1. That's what we're approaching with those numbers. And then looking at the graph for those values at 0, right? Right here, the y-coordinate is 2, right? So that's what we get when x is 0, y is equal to 2, right, on the graph. For negative 0.5, that'd be about right here. We look up here at the graph for that point, which is located right here. The y-coordinate is again 2, right? For negative 0.9, we look at the graph here. For that point that lines up with negative 0.9 on the x-axis, it's really close to negative 1, and it appears that the y-coordinate there is also 2, and we're going to get 2 again here. So f of x is approaching 2 from the right-hand side, right? So as we approach negative 1 from the right-hand side, the f of x values, the y values, are continuing to stay at the value 2. So the right-hand limit here is 2. Sorry, I don't know why it got garbled like that. Let's try that again. All right, so because they are in agreement, right? The left-hand limit agrees with the right-hand limit. So because these are the same, this limit exists this time, right? So this is the general two-sided limit, the general limit as x approaches negative 1. Since the left-hand limit agrees with the right-hand limit, that's going to be our limit for that function. It's going to be 2. So as long as these are the same, that's the answer you have for the general limit as x approaches negative 1. Now, what is f of negative 1? Now, be careful about this because you might intuitively assume that the limit as x approaches negative 1 for f of x should equal f of negative 1. Like those should agree with each other, but they don't always agree with each other. But they happen to agree in this case, right? So I'm going to erase my graph because, the markings I made over here because it's just kind of hard to see. But now we want to look at what is f of negative 1? Again, this means x is equal to negative 1. We find that on the x-axis over here, which is right here. And then we look for the point on the graph with that x-coordinate, which is this point right here. The corresponding y-coordinate for that point is 2. So we happen to get 2 for that as well. But that won't always happen. So I just want to make that clear. Don't assume that the limit value is what the function is equal to at that same x value. All right. So I have down there at the bottom, consider the same problem at x equals 0. I don't know if I want to do that. We're already, I don't know how far into the video. 19 minutes it looks like. So I don't know how long it's going to take. Maybe we could try to do it quickly here. So I'll scroll down. Hopefully you can see everything I'm writing on the screen. So if we consider the limit, and maybe I can do this without filling out a chart. Let's just kind of do it a little bit more intuitively. I want to know the limit as x approaches 0 from the negative side, from the left-hand side. And I want to know the limit as x approaches 0 from the right-hand side. Now, from the left-hand side, I just feel like we should make a chart because I think that's kind of the point I want to make here. So we'll make a chart. as x approaches 0 from underneath, from the left-hand side over here, we can start at like -1, -0.5, -0.1. That's approaching 0, right? It's getting closer and closer to 0 from underneath, from the left-hand side. And what I don't want to do is spend a lot of time like identifying the values. It's these numbers here. The y-coordinate's 2 every time, right? 2, 2, 2. So it's approaching 2. It's just like these problems over here. So I don't want to belabor that point. From the right-hand side, it's a little bit different, right? So from the right-hand side, we want to start above 0. So we'll start at 1. That's kind of how we've been doing this. And then we'll kind of work our way down. So 0.5, 0.1. That's going to get closer and closer to 0, but from the positive direction. But this time, it's not the same answer for y every time, right? In fact, 1 was kind of a bad choice here, right? Because 1, well, it's not really a bad choice. It's defined right here, but it's not on the graph that we have here. So it's kind of, the pattern's actually not going to be as solid as I hoped it would be. But if we start at 1, on the graph, the y-coordinate is 2. So I'm sorry, that is the same. But then for 0.5, that's going to be right here, halfway in between 0 and 1. That's going to be this point right here, which I would estimate, because this is y equals 1 here, that's y equals 2. That's about halfway in between. It's going to be about 1.5, right? So it's not the same value every time. For 0.1, right, it's going to be even closer here. If you look at that value, it's pretty close to 2, but it's underneath 2. So it's somewhere in the neighborhood of like 1.9, right? Now this 2 doesn't quite line up with the pattern here. So maybe we should have done something like more like 0.9. So something close to 1 so that it's on this part of the graph right here. That's going to be down here pretty close to y equals 1. It's going to be about, I'm sorry, I squeezed it in there. It's going to be about 1.1. And maybe we could just ignore that one since it's kind of on a separate part of the graph. So if we start at 0.9, that's pretty low here. It's pretty close to y equals 1, right? So 0.9 is about like just a hair to the left of 1. That's going to be this point right here. And then the y-coordinate's just above y equals 1. So I'm going to estimate it at 1.1. For 0.5, it looks like it's at about 1.5. For 0.1, it looks like it's about at 1.9. And so if you consider that trend, it's also approaching 2. It's not the same. It's not already at 2, but that's the direction it's heading, right? It starts off kind of low, close to 1, then it's at 1.5, then it's really close to 2. And as we keep getting closer and closer to 0 with our x values, those y-coordinates are going to get closer and closer to 2. 1.9, 1.99, 1.999. And so it's going to be 2 as well. And so does this limit exist? The general limit, yes, right? Because these agree with each other, the general limit's going to be 2, right? Okay, let's look at another example. So here, we're looking at positive 2, right? Which is right here on the x-axis. We want to approach it from the left-hand side, so from over here. Again, we can make a chart, but I think we can see the value every time that we're going to get is -1, right? The y-coordinates are -1 every time. So make a chart if you need to, right? You want to start to the right of 2, so you might start at like 1. And then you want to start heading towards 2, right? 1.5, 1.9, 1.99, right? You're getting closer and closer to 2. But for all of those numbers, right, for 1 and 1.5 and 1.9, those all occur right here between 1 and 2. And because that's a horizontal line, it's the same y-coordinate every time, which I know it's kind of hard to read here, but it's at -1, right? That's the y-coordinates there. So it's going to be -1 every time. And so that's approaching -1. Right. For x approaching 2 from the right-hand side, so if I start over here, right, and I'm looking at starting on the right-hand side of 2, I might start at 3, and then start working my way back towards 2, so 2.5, 2.1, 2.01, right? All of those numbers, let me pick a different color here, all of those numbers occur right here on the x-axis. And the graph here is also flat, right? It's the same y-coordinate every time. So I don't know why it's doing that. Okay. which is, looking over here, it's going to be positive 1, right? So for all of these x values, these points have a corresponding y-coordinate of 1. Every single one of them do right here. So it's going to be 1, 1, 1, 1. So this is approaching 2 from above, from the right-hand side. And since our y values are always equal to 1, it's approaching 1, positive 1. These do not agree with each other, which means this limit does not exist. Now, even though that limit doesn't exist, I was going to say, there could be an answer to this, but this time they actually set it up so there's no answer. This is actually undefined. And the reason this is undefined, again, is not because that limit doesn't exist. These are really kind of two different facts. It's undefined because we have open circles on both of these, so that kind of tricked me. I was expecting one of these to be filled in, right? But f of 2 just doesn't exist, because when you go to 2 on the x-axis, even though the left-hand limit exists and the right-hand limit exists, at the number 2 itself, it's open circles everywhere, so nothing's filled in, so there's no y-coordinate that goes with x equals 2, so therefore there's no answer for that, so it's undefined, right? Let's take a look at another example. So there's a lot of these on the homework. This time, we're looking at positive 3. So 3 is right here on the x-axis. So this is one where it's actually filled in somewhere else. So we want to approach 3 from the left-hand side, so from over here. So we'll pick x-coordinates over here, getting closer and closer to 3. So I'll start at 2, right? Start at x equals 2. Again, we're going to have to estimate here, but we'll do 2.5, 2.9, 2.99, right? We're trying to get closer and closer to 3 from the left-hand side, from underneath. And it's not a horizontal line this time, so those values are going to progress towards something, right? They're going to change, but towards a particular answer, right? So at x equals 2, that one we can easily tell. That's this point right here where x is equal to 2. The y-coordinate is also 2, right? So that one we don't have to guess. For 2.5, that's going to be about halfway between 2 and 3. That's going to correspond to this point right here, which to me looks like it's about halfway between 1 and 2, right? So if you look to the y-axis over here for that point, it's about halfway between 1 and 2. So we're going to estimate that's at 1.5. Right? For 2.9, that's going to be really close to 3. So it's going to be about right here. That'll correspond to this point on the graph. So that x-coordinate exists on the graph here. The corresponding value for y at that point looks like it'd be pretty close to 1. I'm going to estimate it at 1.1. Right? And I don't know if we want to try to do this one. 2.99 is even closer to 3. It's going to be even lower here, which means it's going to be even closer to y equals 1. So I'm going to say 1.01. So what is the progression here? What are these values getting closer and closer to? They're getting closer and closer to 1, right? It started at 2, then we got to 1.5, 1.1, 1.01. It's going to keep getting lower and lower, closer to 1 as this gets closer and closer to 3. So this is the limit. The left-hand limit is 1. For the right-hand limit, maybe I'll switch colors for that. We want to approach 3 from the right-hand side of 3, so from over here. So I'll start at 4, for example. And then from there, I'm going to try to work my way back to 3. So I'm going to try 3.5, 3.1, 3.01, right? Getting closer and closer to 3. At x equals 4, the graph almost kind of stops there, but it hits the x-axis, which means the y-coordinate is 0. Right? The y-coordinate is 0 here. At 3.5, that's about halfway between 3 and 4 on the x-axis. We find that corresponding point on the graph right here, and then look at the y-coordinate for that point, which is about halfway between 0 and 1. I'm going to estimate that at 0.5, right, 1/2. For 3.1, it's going to be pretty close to 3 right here. That'll correspond to this point, kind of close to that open circle. And if we look at the y-axis for that point, it's going to be really close to y equals 1, but just underneath it, I'll estimate that at 0.9. For 3.01, same thing, even closer to 3, puts it even higher up, closer to that open circle, which gets it even closer to y equals 1. So let's say 0.99, right? We're going to get even closer. So what's the trend here? These values are getting closer and closer to 1, right? We started at 0, then we went to 0.5, then 0.9, then 0.99. It's going to get closer and closer to 1 the closer we move to 3 for the x values, right? The y values get closer and closer to 1. And so that's the right-hand limit. Because these agree with each other, that means this, general limit exists and will have the same value. It's also going to equal 1, right? So whatever these agree on, that's what the general limit is equal to as well. However, and they're doing this on, these situations are confusing on purpose because they're trying to drive home that point that these aren't necessarily always going to be the same. They're not always going to agree with each other. And they don't in this case, because f of 3, they pulled a little magic trick here, right? And they decided, even though the normal graph would have this point here, they decided to pluck that point out and move it somewhere else, right? So the limits still point to that value of 1 as being the answer on this graph for y. But because they did a little magic trick here and moved the point somewhere else, f of 3 doesn't equal 1, right? They moved that, right? So f of 3, here's 3 right here. I should use a different color, I guess. Here's f of 3. The point that corresponds to x equals 3, I'm saying f of 3 is right here. I apologize, it's late, I'm tired. X equals 3 is right here. That corresponds to this point on the graph, right? Right here, not the open circle, right? That point was removed. And instead we have this point up here, which is the closed circle. And the y coordinate for that point is 2. So this is actually equal to 2 because the point was bumped up somewhere else, right? So the limit may not always equal the function value because they can do little tricks like this, right? Okay, so hope that made sense. If not, let me know when we meet for class next week. Okay, so here are some properties of limits. I about said logarithms because that's what I'm used to saying in college algebra. These are a bunch of properties of limits. I'm not going to go through them one by one. You can pause the video to write them all down. We're going to use a couple of these on the next example. And so I'll just talk about them when we use them on the next example. All right. So this time we want to find the limit of a polynomial with, multiple terms. And so we can break it down using those properties on the previous page. So first of all, we're adding two terms together. We do have this property here that says if you're adding two, we can think of the terms as different functions. If you're adding two functions together and you're trying to take the limit of that summation, basically you can distribute the limit. I know it's probably not the proper way to think of it, but that limit can be applied to the functions individually, right? So we can take the limit of just f of x and the limit of just g of x, figure out what those are equal to, and then add the results together, right? So that's what we're going to do here. So I'm going to apply this limit as x approaches -8 to the 9x and to the 4 separately, and then we'll add the resulting limits together, right? And so we'll get the limit as x approaches -8 of 9x plus the limit as x approaches -8 of 4. And maybe I should use parentheses here. All right. Now let's do this second one first because that property is right at the top of this list here. If k is a constant, if there's no variables, if it's just a number, then the limit is just equal to that number, right? So the limit as x approaches c of any number k is just going to be k. If there's no x in that expression, if it's a constant, it just stays the same. And that's what we have here, right? 4, there's no x in that expression, it's just the number 4. According to that property, this will just equal 4, right? So the limit of a constant just equals that constant. Whatever, it doesn't matter what x is approaching, right? X could be approaching -8, x could be approaching 0. That limit is just going to be that number, right? For this one, we're multiplying 9 times x. So let's see if we can find a property here that kind of matches up to that situation. I suppose it would be this right here. That if we have a constant that we're multiplying to our function, we can bring that constant outside the limit, right? Which is what they're doing here, right? That constant doesn't affect, like, I don't know how to say it. It's just the limit doesn't change that number, so that number can just go outside the limit, right? And then we can focus on just finding the limit of the function, of the variable part of it, right? So this is only true for multiplication. So we're going to do that here with the 9, right? That's a constant being multiplied to x. That constant can just be brought outside the limit because the limit doesn't really care about it. It's not going to change that number in any way. So we'll have 9 times the limit as x approaches negative infinity. Not negative infinity. Why did I say infinity? Like I said, it's pretty late. So limit as x approaches negative 8 of x. It just must be, from when I took calculus 20 years ago, the limit as x approaches infinity. That it's just a really common limit to take. So that's just what popped into my head. And 8 kind of looks like infinity. So, and we'll copy down the plus sign here, right? And then there's one other property on this list that tells us how to evaluate this limit here if it's just x, right? And that is this one here that I kind of covered up, right? So this one right here. So the limit as x approaches c of if it's just x and there's no other math going on, just the variable x, it's just equal to whatever the value you're trying to approach with x. I don't know if I'm saying that right. So it's just equal to c, which is the value that x is approaching. I think that's a better way to say it. So whatever value x is approaching, that's what the limit's going to equal if all you have is x in the limit. And that's exactly what we're dealing with here. The limit, the value that x is approaching is negative 8, and so this is just going to equal negative 8. Since we only have x in here, whatever value x is approaching, that's what the limit's going to equal. We'll copy the 9 down, which is still getting multiplied to that result, and we'll copy down the plus 4, and now we have to do a little bit of arithmetic here. Order of operation, we multiply first, so that's going to give me negative 72. That came out kind of weird. And then plus 4, that's going to give me negative 68. And so that would be the limit as x approaches negative 8. Now, you could say, Mr. Fallon, you're way overcomplicating getting this answer. Because if you go back to this and you just plug negative 8 into that, you'll get negative 68. But again, there could be cases where trying to take that shortcut gives you one answer, but when you apply the rules for limits, you get a different answer, right? So I would be very careful about that and apply the rules that we have on that previous page to evaluate these limits to make sure you're going to get the right answer, right? Okay. In fact, well, I'm saying that now, but I think if it's not in this section, it's in a later section. We will talk about, or it might be this section, the limit of a polynomial really is just plugging that number in. So we probably we're going to have another rule that says you can take that shortcut if it's a polynomial. If it's like a square root or an absolute value, then the rules change. But for polynomials, that is actually a shortcut that will work. Okay. In fact, it's on this page right here. Okay. So limits of polynomials and rational functions. The limit as x approaches c of f of x equals just f of c. So basically, you just take whatever value x is approaching, you plug it into your function for x, and that will tell you what the limit's equal to. But that only is true. I'm not trying to cross that out. I'm trying to underline it. That's only true for polynomial functions, right? That is not true for other types of functions. And what makes it a polynomial function, there's, just to keep it simple, the exponents have to be positive whole numbers, right? If x is raised to the 1/2 power, that's not a polynomial anymore. If x is raised to the negative 2 power, that's not a polynomial. The exponents can't be negative. They can't be fractions to be polynomials, right? If it's a rational function, now a rational function is a function of the form p of x over q of x. I believe we talked about these in chapter 1, but it's one polynomial divided by another one, so it'll be a fraction, right? It works the same way, right? Whatever value x is approaching, you plug that in to your rational function, and that will tell you what the limit's equal to. as long as you're not dividing by 0 when you do that, right? So if you plug x equals c into that rational function, and it makes your denominator equal to 0, then you can't evaluate the limit this way, right? Okay, and I think we'll have some other rules for dealing with that. All right, so let's look at an example. This is a polynomial. It's factored, but it's still a polynomial. If you would like to make it look more polynomial-ish, we will distribute the x, right? And we'll get x squared minus 2x, right? That's what polynomials tend to look like. So this is a polynomial. The rule that we just discussed tells me I can get this limit by taking the value that x is approaching and plugging it in for x. So I'm going to get 5 squared minus 2 times 5, and then I just evaluate that. It's going to be 25 minus 10, which is going to be 15. All right. So easy peasy, as long as it's a polynomial. So you don't have to do anything complicated like making those charts and seeing what happens when I plug in 4.1, 4.5, 4.9. We don't have to do all that. This gives us a really nice shortcut to getting that answer. And we don't have to check the left-hand limit and the right-hand limit. This rule basically guarantees that limit definitely exists, and this is the value that would be agreed upon. So if you did the left and right-hand limits, the value that they would agree upon is 15, right? But we don't have to do all that work. We're being guaranteed that it works out just fine. Here, this one looks a little iffy, right? You're taking -3, and this is a rational function, so the rule works basically the same way. The limit should equal the result you get when you take this value that x is approaching and you plug it in for x. As long as it makes you, how do I want to say this? As long as it does not make you divide by 0, which this looks like it might, but it doesn't, right? So we're going to plug in -3 for x. We'll get -3 squared minus 7 on top. And on the bottom, we'll get 3 minus, and in place of x, we're going to plug in -3. And because it's minus a negative, that's going to be positive, right? So this will be a plus here. And then -3 squared is positive 9. So that's going to evaluate to 2, right? 9 minus 7 is 2. And here we'll get 3 plus 3, which is 6. As always, you want to reduce your fractions. So 2 over 6 reduces to 1/3. And that would be our limit in that case. All right. I want to keep moving along because our video is already at 42 minutes. I'd like to try to keep it to 50 minutes is kind of my goal here. So I'm sorry, I'm not going to have time to edit this, so I'm sorry. It's not going to be a very polished video. Okay. So here, I'm sorry, it's kind of hard to read this, but we have part A, part B. Sorry, I hit the microphone again. Part C and part D. Right. And we're doing this for a piecewise function, and it gets a little wonky here because, of course, the value that we're having x approach is right on the boundary of these two functions, right? When x is less than 0, we use one equation. When it's greater than 0, we use the other equation. And so we're going to have to kind of split between those two because we're concerned about what's happening right at x equals 0, right? So, and be careful on the homework. Don't assume that the first partial limit here is always the left-hand limit. Part A is actually asking us to find the right-hand limit first, which means we're trying to approach 0 from the right-hand side. So if we want to make, so this time we kind of have to make a chart again. The right of 0, again, if you think of the real number line, here's 0. To the right of it, we have 1, 2, or whatever. You don't want to go that far away from 0. We'll start at 1. And then from there, we want to start heading back to 0 incrementally, approaching it, getting closer and closer, but not getting all the way to 0, right? So 0.5, 0.1, just the same kind of choices we were making before. Now, what we're going to have to do this time, instead of reading it off a graph, is we're going to have to plug it in to this piecewise function, but we have to make sure we plug it into the right part of it. These values are positive. They're greater than 0, right? They're to the right of 0, so they're greater than 0, which means this is the condition we're satisfying, right? All of these numbers are greater than 0 because they're positive, which means we want to use this leg of the equation, which is right here. So these values of x need to get plugged into the bottom equation to get the y values. So let's go ahead and do that. We will have 1 plus 1 squared, which is going to give me 1 plus 1, which gives me 2, right? When I plug in 1 there. 1 plus 0.5 squared, that's going to give me 1 plus 0.25, which gives me 1.25. So again, use a calculator if you need to. 1 plus 0.1 squared gives me 1 plus 0.01, which gives me 1.01. 1 plus 0.01 squared is going to give me 1 plus 0.0001, which is going to be 1.0001. And so what value are the y coordinates approaching, right? The x coordinates are approaching 0. We made sure of that by the choices we made. The y coordinates appear to be getting closer and closer to 1, right? And so this this right-hand limit is equal to 1, positive 1. Now, for the left-hand limit, we're going to do the same thing. We're going to make a chart. See, I guess I'll do it underneath. I feel like I'm running out of room here. On the right-hand side, I want to go this way a little bit too. Okay. And I'll switch colors just to make this a little bit easier to read, hopefully. So we're going to do the same thing. We'll make a chart. This time, we're approaching 0 from the left-hand side. So 0 is right here. The left-hand side of 0 is -1, -2. So we'll just kind of start at -1 and then slowly work our way back to 0. So we'll try like -0.5, -0.1, -0.01. Getting closer and closer to 0, right? That's what we're approaching there. Because these values are less than 0, we will need to use this, how should I say this? These values satisfy this condition, which means we need to use the top equation to get these answers, right? So I'm going to take the top equation, which is 1 minus x squared, and then I'm going to plug in these values for x. It gets a little bit messy. I think they did this to us on purpose with all these negative signs, right? We have a minus sign in our equation, and then we have to plug in -1 for x. So be careful in how you simplify this. -1 squared gives me +1, and then 1 minus 1 is going to be 0. So we get 0 here for y. 1 minus -0.5 squared. The negative is going to get canceled out, so we get 0.25. 1 minus 0.25 is going to be 0.75. Okay, so we get 0.75 here. Okay, so again, you can use a calculator if that was kind of hard to follow, but this is positive 0.25. This minus sign copies down, though, so we still end up subtracting. 1 minus -0.1 squared, that's going to be 1 minus 0.01. Again, this is positive 0.01, but then that minus sign copies down, so we get 0.99. And I'll leave it to you, but for this last one, you should get 0.9999, I'm pretty sure. And this one I think is even more obvious. What are the y values approaching? They're getting closer and closer to 1, right? 0.99, 0.999, right? So the left-hand limit is equal to 1. I'm going to scroll back up so we can see our previous answer. And we see that they agree with each other, right? These are in agreement. I don't know how I'm going to spell agree here. I guess out of order, but agree. And since they agree, the general limit, the two-sided limit, as it was called earlier, I don't know why I'm saying general, but the overall limit exists because these agree, and it's going to equal the value that they agree on, which is going to be 1, right? And then they want us to find f of 0. If we're going to plug in 0 for x is equal to 0, we see that condition is satisfied here, so we're supposed to use this equation here. So it's going to be 1 minus 0 squared, which will be 1 minus 0, which is going to be 1. And so this is also equal to 1, so everything here equals 1. If there was a simpler way to figure all that out, I would tell you, right? But that is the way you have to approach it. There's no way to know ahead of time that we're going to get the same answer for all 4 of these. All right. So we're hitting the 50-minute mark. Let's see how many more examples do I have here. A bunch of piecewise. And I might not do all of these. I kind of feel like, I don't know. These actually are different. These are different. So maybe these are worth doing. This one kind of the same thing. So I think I'm just going to skip this one. Yes, there's a square root in there, but really the breakdown's exactly the same. I'm guessing that these limits, like this limit, doesn't exist because these probably don't agree with each other. Maybe I could just tell you what you should get. So what I believe you will get here is, as you approach it from the right, that would be using this one, you're going to get closer and closer to 2. I think this should equal 2. And you're going to be using this bottom equation to get that. As you're approaching it from the left-hand side, that's less than -2, you're going to use this equation for that one. And what I think you're going to find is that it's going to approach 4, right? And I'm kind of cheating here because, I'm basically, plugging that number in. -2 plus 6 will be 4. So as we get closer to -2, you're going to find your answers are going to just get closer and closer to 4. These do not agree, right? Which means this limit does not exist. Right? So the overall general two-sided limit of just x approaches -2 will not exist since the left and right-hand side limits don't agree. But this still has an answer, right? So we can take x equals -2. No, it doesn't. Oh, it tricked me again. There's no equals 2 here. So actually, this doesn't exist either. But again, it could. If there was an equals 2 here, this would still have an answer even if the limit doesn't exist, right? So I just want to make that clear. Since it doesn't have an equals 2, they've tricked me again. I've tricked myself, I guess. And this is undefined, right? Because neither one of these has an equals 2. So we have nowhere to plug in -2. It doesn't satisfy either condition. We need an equals 2 there for that to happen. So those are the answers you should get. If you're not quite sure about how to arrive at those results, again, let me know when we meet for class, and I would be happy to answer your questions. This one is not asking us to do left or right hand limits. It's just asking for the overall limit as x approaches -12 of f of x. -12, right, is less than 0, right? So this x value that we're approaching is less than 0. It's not even on the boundary, right? It's clearly less than 0, which satisfies this condition, which means this is the limit that we want to evaluate. Are we ready for this? I don't know. I don't think I've talked about this yet. Because when you plug in -12 here, you're going to divide by 0. So I guess we just say the limit doesn't exist, right? Because the condition it satisfies is this one. Now, it would exist here, but we can't use that equation when x is less than 0. We have to use this equation here. And the problem with that is the rule that we learned earlier is it's a rational function. So we can just take the value that we're given here and plug it in for x. Now, the thing is this reduces. So I'm not sure, honestly, if we're supposed to reduce it and then evaluate it, because then you would get an answer, or if we're supposed to just kind of leave it as it is. I feel like I'm not sure. I really am not, because at some point we do want to reduce. I do remember as I was putting the notes together, we are going to be asked to reduce the fractions to evaluate these limits. But I don't know if we're supposed to be doing that here. So because the reason this reduces is because x squared minus 144, that factors as x plus 12x minus 12. Right? And then that x plus 12 can cancel out with this x plus 12. So really, you're not going to end up dividing by 0 because it'll get canceled out. You're left with x minus 12 here, which you can plug -12 into, and you get -24. If I had my math lab up, I would pull up this problem because I grabbed it from the homework, and I would just check to see what the answer is that they're expecting to know if we should reduce it or not. If we are not supposed to reduce it, if we're supposed to evaluate it as is, then the limit doesn't exist because we're dividing by 0, right? I'm trying to think. Okay, so indeterminate form. Yeah, so that's using this rule here, right? If the limit on top is not 0, but the limit of the denominator is 0, then the limit of the rational function with those two does not exist. And that's what's happening here. And that's assuming we don't reduce it, right? The limit on top is fine. It's 0. Actually, it's 0 too. It's 0 too, actually. So what am I saying? It'll be 0 as well. So does it say something about that here? It doesn't. Okay. I think we're supposed to reduce it then. I think we are supposed to reduce it. So reduce this. The x plus 12s cancel out. We're left with x minus 12. And then you can plug negative 12 into what's left over here. And you'll get negative 12 minus 12, which is negative 24. So I'm going to make that call. If I'm wrong, if you do this problem on the homework and that ends up being wrong and it's supposed to be does not exist or whatever, I apologize and I'll stand corrected and I'll make sure I do better next time. But I'm going to go with that. The same thing happens on part C, right? Same dilemma, right? Here, x is greater than 0, right? So we want to, it satisfies this condition, so we use this equation. Again, this numerator factors as x plus 12, x minus 12. The denominator is x minus 12. So we reduce it first, right? The x minus 12s cancel out. You're left with x plus 12. It's a polynomial. So the rule is you can just take this number, plug it in here for x to get the limit, right? And the limit's going to be 24. Sorry, that came out kind of funny. 12 plus 12, which gives me 24. So I'm going to make that call. Again, if I'm wrong, view the example on my math lab. If my math lab, the example says these should be does not exist, then that's what you should go with. When x is equal to 0, now this one is not equal to 0, but as x approaches 0, this one's kind of tricky. So first of all, this function is not defined where x is equal to 0, right? There's no equals to here. But there still could be a limit if these agree with each other. But we have to check. So this one we actually have to check the left-hand limit and the right-hand limit. The left-hand limit will be as x approaches 0 from underneath, which will be when x is less than 0. Excuse me. Which is this equation up here on top. And what I'm going to do here, I'm just going to use a shortcut. Let's reduce it, right? So this reduces to x minus 12. And then what's going to happen is, since that's a polynomial, as x approaches 0, you just plug in 0 for x, right? Even though it's a left-hand limit, just plug in 0 for x here. Sorry, let me use a different color. 0 minus 12, which gives us negative 12, right? So the limit of this function, using the top equation, approaching 0 from underneath, from the left, is going to be negative 12. The limit from the right, as x approaches 0 from the right-hand side, we have to use the other equation, because this is where x is greater than 0, right? These are going to be positive values of x as we're approaching 0 from the right-hand side. We want to use this equation, which reduces to x plus 12. We plug in 0 here, we get 0 plus 12, which will be positive 12. These do not agree. And so this limit here does not exist, because the left and right-hand limit don't agree with each other. All right, I hope I got part A and C right. I'm very confident about part B. Okay, so kind of maybe I got my examples out of order here, because what we just experienced was this exact thing, an indeterminate form. And I'm pretty sure I remember reading in the book that if you're trying to find the limit of a 0 over 0 indeterminate form, it often involves simple algebraic simplification, which means reducing the fraction, which is why I think that was the right thing to do on the previous problem. Reduce it first, then evaluate the limit after you've reduced it. If you get 0 divided by 0 without reducing it, right? So if you don't reduce it and you get 0 divided by 0, reduce it first and then try to evaluate the limit after that, right? And so this is the case where the limit as x approaches c, for the numerator, that approaches 0, and the denominator, that approaches 0. So basically what happens when you try to evaluate the limit is you get 0 divided by 0. You don't want to say, like, you might think, oh, you're dividing by 0. That means the limit doesn't exist. But because it's 0 divided by 0, it's indeterminate, meaning you don't know whether the limit exists or not. You have to evaluate it further, which will involve reducing the fraction first, and then come back to it and try to evaluate the limit after that. You cannot call it at this point, right? If you're getting 0 divided by 0, it's indeterminate. The answer is unknown. You have to investigate further, using another rule. Or, like I said, reducing the fraction. All right. However, if the numerator does not go to 0, so it's saying if the limit of the numerator is equal to L, where L is not equal to 0, it's equal to something else, but the denominator, the limit does go to 0, then you're getting L divided by 0. That is undefined, right? And in that case, it is determined, right? It is determinate. The limit doesn't exist in that case, right? So if the numerator also has a limit of 0, then you can't tell. You have to investigate further some other way. Like I said, reducing the fraction, for example. But if only the denominator is equal to 0, then you know the limit doesn't exist. Okay. So let's see. I have just a couple more examples, just 3 more pages. But this thing, there's 2 examples on this page, and yeah, it looks like a lot to consider. All right. So here, as x approaches negative 11, right? Let me pick a different color. That's less than 0. That satisfies this condition, which means we use this equation. Now, the limit, as this approaches 0, we can evaluate by just taking negative 11, because it's a rational function, and just plugging it in for x, right? And so on top, we'll get 5 times negative 11 over negative 11 plus 11. This time, we get negative 55 over 0. So the limit of the numerator is negative 55. The limit of the denominator is 0. Since the numerator isn't also 0, we know that this limit does not exist. Right. Unlike, and I didn't really, what am I doing? I'm hitting the wrong button. Unlike on this page, and I'm sorry I didn't really, this became a giant mess, but if you plug negative 12 into the top and bottom here, right, we could have tried that first. I abandoned it because I kind of saw what was happening. But if I plugged in negative 12 on the top and bottom here, and you see the limit here is 0, right? That's going to go to 0. But this will be positive 144. 144 minus 144 is also 0. So we get 0 divided by 0. That is the indeterminate form, which means you cannot draw an answer from that. You cannot tell whether the limit exists or not from that result. So in that case, you want to reduce it. In fact, I remember reading in the textbook somewhere, if you get 0 divided by 0 as your limit, that is resolved by reducing the fraction, which is what we did here. We factored it, canceled out the common factor, it left us with x minus 12, and then with that, we could figure out what the limit was. All right. Okay. But here, it's not 0 divided by 0. It's some other number divided by 0. That one we can just draw a conclusion right away. The limit doesn't exist in that case. The same thing happens here, right? Here x is greater than 0. That satisfies this condition. We use this equation. If you plug in 11 there, you get 55 divided by 0. Same issue, right? So this limit doesn't exist. This one also does not exist. For x equals 0, even though that's not a defined value on this function, we can still evaluate the limit, but we have to check the left and the right-hand side like we did on the previous example. Excuse me. Okay. So it's kind of like the last problem. I kind of feel like I'm really tired. I'm ready to be done. So I'm like, I don't want to do this. It's like the last example, but I'll try to tough it out. So here we'll have the limit as x approaches 0 from the left-hand side. That's where x is negative. So I'm not going to write out all the same things I did last time, but from the left-hand side is where x is negative. So we want to use this equation to evaluate it. And we're just going to plug in 0, We're just going to plug in 0 because it's a rational function, and that's how you evaluate a limit for a rational function. You plug in the number that x is approaching. You plug that in for x, right? So we're going to plug in, so this is going to equal 5 times 0 over 0 plus 11. Now this time we get 0 on top, but that's fine. 0 divided by 11 is just 0. So the left-hand limit is going to be 0. Let's check the right-hand limit, right? Because in this case, it's positive. We want to use this one because it satisfies this condition. We're going to plug in 0 to this equation, right? So we'll get 5. So this limit, I'm leaving out the f of x part here. I'm being lazy. 5, f of x. It's going to be 5 times 0 over 0 minus 11, but same thing. It's going to be 0 divided by negative 11. That's still 0. So the right-hand limit is also 0. Because these agree, this limit does exist, and it equals the value that the left and right-hand side limit agree on, which is 0. All right. Now this one, I'm just going to go ahead and skip this one. I'll just leave that. You'll see something similar to this on the homework. If you have trouble with it, just let me know. We can come back to it. This video is already over an hour. I apologize for that. We have this one last topic. And this is a very important topic, actually, even though it's at the end of this video. We're going to see this again. This is called the difference quotient. And it's a really important formula in calculus. It's f of a plus h minus f of a divided by h. Where you have some function f of x, right? So you're going to plug in a plus h into that function, and that's how you get this part of the answer here. And then you'll just plug in a, which means it doesn't change. You just use a instead of x. And that'll give you this part of the equation here. And then you divide that by h. Now that's the difference quotient, but what we will often do with the difference quotient is take the limit of it as h approaches 0. So really, this part right here is the difference quotient. But it's really common to take this limit of that difference quotient. And you might notice, well, if you're letting h approach 0, and you plug in 0 here for h, you're dividing by 0. So isn't that going to be a problem? But surprisingly, you might be really surprised by this. I know I am. It's really kind of surprising. Once you kind of do the algebra on this, that h kind of disappears most of the time. Not always, but usually it disappears pretty directly. Sometimes you have to do some clever tricks to kind of make it go away, but typically the dividing by h kind of just goes away. And then you can just plug in 0 for h everywhere else, and you get an answer oftentimes, right? So that's the difference quotient. We're just going to practice using it here real quick. So our function f of x is equal to x squared plus 5. In the future, we're going to leave x in here, or we're going to leave a, In this case, we're going to use a number, right? So f of 5, let's start with that one, because that one I think you should be fairly comfortable with finding. You just plug in 5 for x. We'll get 5 squared plus 5. That's going to be 25 plus 5, which gives me 30, right? And so this is equal to 30. So I'm going to rewrite this expression down here, but this part of it gets replaced with a 30. It'll be divided by h, right? The h will still be down there, so I'll go ahead and copy that part down too. Now we need to figure out what this is going to equal. F of 5 plus h. And this one is going to get a little messier, right? So we're going to take the same function, but in place of x, we're going to plug in 5 plus h. Right? So here we'll have 5 plus h. That's going to get squared, right? Because we're going to square that, and then we're going to add 5 to that. Right? Unfortunately, you cannot just distribute this power of 2 to the parentheses. What you have to do is write it out side by side, and you're going to have to FOIL. You're going to have to multiply these together. First, outer, inner, last. Right? So we'll get 5 times 5, which is 25. 5 times h, which is 5h. H times 5, which is also 5h. And h times h, which is h squared. And then we'll have the plus 5, which we copy down there. And then we'll combine like terms, so the 25 plus 5 gives me 30. 5h and 5h gives me 10h. And then the h squared. And it might seem weird to leave it in this order, but you can rearrange it if you want to and have it as h squared plus 10h. But I usually don't bother with it. So because we're about to let h equal 0, h kind of isn't going to matter very much here in just a minute. So that's what we're going to plug in here, right? So this function, when I plug in 5 plus h, gives me this result. So I'm going to put that here, 30 plus 10h plus h squared. And I'm sorry, I'm really doing a bad job of drawing this fraction bar here. Let's try that one more time. Okay, so we have a fraction here. This looks worse. Let's see if I can just erase my first attempt and try to draw it again so it goes all the way across. Okay, that's a lot better. Okay, now we want to simplify, and you'll notice, maybe you've already seen, and we're trying to find the limit as h, it's supposed to be an h, approaches 0. We'll get to that in just a minute. Simplify this first. Right? Notice the 30s cancel out, right? We have positive 30 here, negative 30 here, those cancel each other out. So that's going to give me 10h plus h squared divided by h. Try that again. Divided by h. Now, before we because if we do this now, if we take 0 and we plug it in for h, we'll get 10 times 0 plus 0 squared over 0. You're going to get the 0 over 0 indeterminate form, which just means you can't figure, like, this is not going to tell you what the answer is. You cannot figure out what the answer is from that result. And this also means what you need to do is reduce. Try to reduce or simplify first, and then come back to it with that same approach. So this can be reduced, right? We can take this h and divide it into each term separately, right? So let's go ahead and do that. Reduce it first, and then we'll try plugging in 0 for h and seeing what happens, right? So we'll kind of continue down here. We'll get 10 over h. I'm saying the wrong thing. We'll get 10h over h plus h squared over h. And in the first case, the h's cancel out, and we just get 10. Here, we can cancel out one h, but we'll still have an h left over. So it reduces, the fraction goes away. Now we'll take the limit as h approaches 0 of this expression. And because it's a polynomial, we just take 0, we plug that in for h. We're going to get 10 plus 0, which gives me 10. And now I have a result, and that's the limit as h approaches 0. Okay, so do the best you can with that difference quotient. We're going to revisit that later and do a lot more with it later, so you'll get more practice with it. If it isn't quite clicking for you in 2.1, don't worry. After we practice it a little bit more later in the chapter, hopefully it makes sense. I might keep this video for future times that I teach applied calculus, but I just want to apologize that I wasn't able to be in class to do this lesson. And I'm sorry, because it's our first actual, foray into calculus topics. And I know it's probably going to be confusing. It's going to be kind of a jarring transition. And I'm sorry I wasn't there in person to kind of walk you through it and answer your questions because I'm sure you're probably going to feel a little bit confused or struggling as you're watching this video without a way of asking for clarification. So I apologize for that. But do the best you can with it. And then when we meet again next week, let me know what your questions are. And I'm going to be willing to go back to 2.1, do a few more examples, address whatever questions you have about the material. And then before we move on to the next sections. So, all right, that's it for section 2.1. See you next time.